Hello all, and welcome to the last session in the course Pre-MBA Statistics. Now this entire course has been a flurry of different sort of ideas in, let's say, inferential statistics or basic statistics, probability, random variables, distributions, hypothesis testing, confidence intervals, and towards the end we are focusing more on regression in the last week. Okay. So again, you have to sort of connect all the dots before you sort of put forward a sort of try to please the client that you have. Okay. So when I say please the client that you have, is that if you are trying to analyze a practical data, then right from, let's say, collecting the data, trying to analyze that using, let's say, some basic summary variables, then maybe fitting some distributions, let's say normal distribution, etc., trying to estimate a few ideas, trying to maybe create some confidence intervals, maybe testing some hypotheses, and ultimately when we talk about regression is more like prediction. Okay. So it's an end-to-end sort of a chain that one can sort of follow when you are sort of delving into more on, let's say, analytics or machine learning also, and so on and so forth. So again, like I said, regression is a base of machine learning. Okay. So people start with regression or try to sort of compare machine learning ideas or advanced machine learning models with a simple linear regression model or multiple linear regression model. Okay. So again, before we begin with the last session here, which is of course a practical example sort of a session using case studies, we'll talk about a couple of data sets very soon in this idea. We'll try to connect all the dots we've been discussing this week. But again, just to sort of give you a brief refresher of what we discussed in the last class, okay, or rather the last session, so that there is not a disconnect at your end. So last class, if you remember, we started the session with F test, okay, or rather ANOVA, okay, or analysis of variance. So analysis of variance is a kind of a key ingredient in any regression modeling class or regression modeling exercise. You have to sort of make sure that the underlying hypothesis beta 1 is 0 or beta 1 is not 0 is sort of tested either using ANOVA, using an F test or a T test. Okay. So again, this entire idea has been focusing entirely on SLR, or simple linear regression, where you only have a single x and a single y. So under all these situations, we saw even in the last session that an F test is sort of equivalent to a T test. Okay, so for the same set of hypotheses, beta 1 is 0 and beta 1 is not 0, I can sort of create a single T test for a variable, or I can go for ANOVA and look for the overall structure using an F test. Okay. And then towards the end of last session, if you remember, we talked about diagnostic checking. So you have to ensure that the 4 conditions LINE, namely linearity, independence, normality and equal variance, are met. And again, due to paucity of time, we could only discuss a single plot and 2 problems, essentially linearity or rather non-linearity is a problem and unequal variance as a problem. Okay. And then we took a couple of examples where in the first example things were okay, but in the second example, if you remember the groove versus mileage example, things were not okay. So linearity was a problem there, and that was more starkly seen using the residual versus fit plot. Okay. So firstly, how do you check that? So we created the EI versus the YI hat plot, and there the assumption is that if all the points are randomly lying along that horizontal 0 line, then things are good to go. Otherwise, there might be some problem there. Okay. And lastly, we talked about a very important idea that if you have any problem, let's say if linearity is a problem, independence is a problem, normality is a problem, equal variance is a problem, then what should you do? Okay, so simple understanding there was to you have to transform the model. So either make some transformation on x or on y or on both x and y. Okay, and some of the routine transformation we discussed were log transformation, square root transformation, inverse transformation. So what do you mean by inverse? Inverse means nothing but 1 by x or 1 by y. Okay. So hopefully the moment you make all these transformations, I mean of course either one of all these transformations, either be it log or square root or inverse and many more of course, right, then the hope is that you are sort of correcting the problem in hand, you are moving ahead, you are refitting the regression model in a hope that the line conditions would be met. Okay. So this is kind of a clinical way of sort of approaching a regression modeling analysis or sort of regression modeling exercise there. Okay. Alright, so now the very last session will again pick up, let's say, a couple of interesting data sets, and then we'll sort of create or rather try to create some problems around the data set revolving around, let's say, regression modeling, estimating the parameters, interpreting the parameters, t-tests, f-tests and so on and so forth. And interestingly, the second example we will see today would be more on MLR. MLR is multiple linear regression, so you will kind of understand that how should you sort of extend SLR ideas to MLR as well. Okay. Okay, so we'll begin with the first data set, and then the focus would be simple linear regression or SLR. Now the data set name is faithful data set. So very standard data set, and again like I said, I'm kind of very used to R, the R software. So again, if you're not used to R, the R software, it's perfectly fine. If you have worked with the R software, then you can sort of also try playing around with what we're doing in all the practical sessions, not just this one, but again the earlier ones that we've been discussing as well, because all the data sets and all the practical aspects I am kind of doing in R and then giving you the outputs directly. Okay. So again, for example, this faithful data set is inbuilt in an R package, by the way. So if you are aware of the R software, then you can onboard the faithful data set, you can try to sort of summarize the data or summarize some variables, etc., and just try to play around with what the data set is telling you and so on and so forth. Okay. Alright, anyways, but then what this data set gives you is that the data gives the waiting time between eruptions and the duration of the eruption for the old faithful geyser in Yellowstone National Park, Wyoming in the United States of America. So firstly, this old faithful geyser is a volcano. So you can call this a small volcano, and this is right inside a national park in the US called as the Yellowstone National Park, quite famous volcano itself and quite famous national park itself in the USA. There is so I guess on the annual basis, this is one of the most visited national parks in the United States. Okay, and just by the name of it, it says Old Faithful Geyser. So geyser means some sort of a volcano in play. Okay, and interestingly, this volcano erupts after some time. So it's not like it's erupting every 1,000 years or 10,000 years. Okay, so this is a small volcano. It sort of erupts after regular intervals. Okay. Hence, it makes all the more sense to sort of predict the next occurrence of the volcano, or how much is the waiting time before we will see the next occurrence, and so on and so forth. Okay. So kind of a simple data set, it contains 272 observations only on two variables. So one of the variables is eruptions, which gives the eruption time in minutes, and the second variable is waiting time. Again, both are numeric, and the waiting means waiting time to next eruption, again in minutes. Okay. So the first one is eruption time in minutes. So how much time it has elapsed until it, or rather since it erupted. So the eruption time of the volcano of the Old Faithful Geyser, and on the other hand with the waiting time. So waiting time to the next eruption. So how much time has elapsed between two eruptions of the geyser. Okay. Alright, so just a quick snapshot of the data set. Again, you have many more rows here, but then the key variables are eruptions and waiting time. And again, you can see that both are in minutes, both are numerical. So for example, 79, what do you mean by that? So there has been 79 minutes before the next eruption, or there has been 54 minutes before the next eruption. Okay. So you can kind of see that this volcano erupts at fairly regular intervals, right? So 79 minutes is just slightly above 1 hour, 54 is not even 1 hour, right? So after the first eruption, within the next 1 hour, it has again erupted. Okay. And how long are the eruptions is given by the first column. So 3.6 minutes, 1.8 minutes, 3.3 minutes. Okay. So now just to understand, of course, it's written down the next slide, but the whole idea here, or so where exactly can we bring in the regression modeling? Okay. So we can sort of try to find out the eruption time based on the waiting time, or vice versa. Okay. So based on one of the variables, you have to try to find out the idea about the other variable. Okay. Yeah, so before we sort of give you the exact problem there, some sort of an exploratory analysis. So we'll start with the basic scatter plot. Let's say we're taking eruption duration in minutes on the x-axis, we're taking the waiting time again in minutes on the y-axis. Okay. So here possibly the assumption or the idea is to use the eruption time, which is x, to predict the waiting time, which is y. Okay. So the current eruption time of the volcano or the geyser, and using that current eruption time in minutes, can we sort of predict the waiting time for the next eruption. Okay. And if we are able to do it, then it's kind of helpful in, let's say, crowd management as well. So if you know that so next eruption would occur slightly less than 1 hour. Okay. So we can manage the crowd easily, and again we can sort of do a lot of other things using these conclusions. But then again, the idea is that we can sort of keep this eruption duration as the independent variable, and on the other hand we can keep the waiting time as the response variable. Okay. And here very interestingly you can see that this is a simple scatter plot, and then if you try to draw a line of best fit, which is nothing but the red line we've been seeing in all the examples, it will sort of pass through all the points evenly. So you see that there is not much scatter here. And of course you can see two sort of groupings, right? So one on the left hand side and one on the other side. But regardless of that fact, the fit seems to be decent here, isn't it? I mean, there's not, you don't see any points which are far away from the red line there. So the line of best fit is passing evenly through all the points, and even the scatter is sort of manageable. When I say manageable, the points are scattered along the red line, or rather the points are randomly scattered close to the red line. Okay. So we'll see exactly what's going on here more mathematically. So we'll try to create the regression model and so on and so forth. Okay. Alright, so before we fit an SLR model, we have to understand that why are we doing the SLR first, or what variables are we sort of fixing. So firstly, what would be the independent variable, what would be the response variable, and so on and so forth. Okay. Alright, so from the snapshot we've seen just a couple of slides back, the old faithful geyser erupts every 1 hour to 1.5 hours. We've seen that in the data set on the earlier slide. Okay. So the volcano erupts every 1 hour to 1.5 hours. So the researchers actually want to know that how long should one wait before seeing the next eruption. So again, like I said, it is more for crowd management, in general the crowd management inside the national park, ticketing probably, and so on and so forth. Okay. So again, the researchers want to know that how long should one wait before seeing the next eruption. Okay. That is, one should actually predict the interval, the waiting time, or the interval between any two eruptions based on the previous eruption duration. Okay. So eruption duration would be the x variable here, which is the independent variable, and the interval or the waiting time would be the y variable. Okay. So based on this small information, we can sort of create the regression model in hand quite easily. So the response is waiting time Wi equals beta naught plus beta 1 into EI. So EI is eruption duration plus some random error there. Okay. So again, like I said, once you understand that what variables you have to fix as the predictor variable and the response variable, things are not very difficult later on there. Okay. Alright, so fitting an SLR model, all these things could be done using pen and paper, of course, because you are focusing on SLR. We've seen couple of slides back, not couple of slides, but couple of sessions back, what are the formulas for B0, B1, right? I mean, one can actually use a pen and paper and try to find out B0, B1. Once you find out B0, B1, you can fit the, or you can actually write down the fitted regression model as well. But on the other hand, just to save some time, we can do regression modeling very easily using any software. So be it Excel, R, Python, MATLAB, etc., etc. Okay. Alright, so this is a summary of the fit that's again given by R here. So again, lot of information. Again, of course, we'll not discuss each and every value here, but again, you can see that you have some chunks, right? So different sort of groupings inside the entire bigger table here. At the very top, you can see the actual formula which is being used, right? So firstly, LM. So LM stands for linear model. So this LM stands for linear model. You're fitting a linear model. Now this is more like a syntax in R. So what exactly is a response variable? Waiting time is a response variable. Eruption duration is the predictor variable, and data is a faithful data. Okay. So this is exactly how you fit a regression model in R. So you basically take y tilde x. So whatever y you have, in this case waiting, tilde whatever x you have, in this case eruptions. Okay. And once you write this single line of code in R, it should give you the table that you see here there. Okay. Now again, the first chunk gives you residuals. So how are the residuals behaving? Residuals means which value? So EI values. EIs are nothing but yi minus yi hat values. Okay. So what is the median residual? How much is the minimum residual, maximum residual, first quartile, third quartile, etc. So as of now, we are not very much concerned about this part of the table here. But now the most important part in this entire table is the coefficient chunk. Okay. So if you see, you have two rows here. The first row gives you intercept, the second row gives you the actual x that you have, which is eruptions. And then similar to how we saw the ANOVA table in the last session, you have several columns here. So the first column is kind of important to us, the estimate. Okay. So 33.47 in our case, or this example, is nothing but B0. So 33.47 is the intercept, while my B1 is nothing but 10.72. Okay. So the one corresponding to intercept, of course, is B0. The one corresponding to eruptions, or whichever x you have in the data, is nothing but B1. Right. Then the standard error, then the t-test statistic values, and finally the p-value. So again, the p-values are also important. So we should focus more on the second p-value here. okay, because again remember we are interested in beta 1 more and not beta 0, right. And of course, this table gives you p values for both beta 0 and beta 1, I mean assuming you want to test for both beta 0 and beta 1, but we are not concerned with beta 0, right. We discussed this number of times even in the last sessions. We are concerned more about beta 1 being 0 or beta 1 being not 0, okay. So, we can look at the second p value here and we can see very evidently that the second p value is again very small, right, less than alpha. By the way, how do you read this? So, 2e minus 16 means 2 into 10 to the power minus 16. So, e stands for 10 to the power minus 16. So, very small value here, which is of course less than 5%, which is alpha, if you fix 5% as alpha. And hence the conclusion is that the significance between x and y is decent, or you have a significant relationship between x and y, okay. And again we will come back to how do you interpret the estimates very soon, but the last chunk that you see again contains a lot of information, and couple of key information that we require is this guy, which is 0.8115, which is nothing but the r square value, okay, the capital R square value or the coefficient of determination. And here you can see that the r square value is close to 1, so hence the fit is good, and so on and so forth. And of course, the last row, the entire last row gives you the conclusion coming from the ANOVA or the F statistic. And here as discussed in the last session as well, that you should get the same p value that you are getting for the t test, right, because since you are fitting an SLR model, right, t test and F test are exactly same, okay. So, the p value you will get from a t test from the summary table or the coefficients table should be exactly same as the p value that you are getting from the ANOVA from the last row of the table, okay. So, again I will say that every software has a way of reporting the summary of a regression model, and then there might be slight changes here and there, but again since I am kind of used to R, I am kind of presenting the exact same thing, okay. But I will try to explain the key, or rather I have tried to explain the key elements of a summary table, and let us say if you are working in some other software, just try to play around with the faithful data and try to see that what do all the numbers mean, okay. Alright, so again we can sort of borrow a lot of information from the last table that we saw, and eventually we can write the fitted model here, okay. So, this is the fitted model. So, Wi hat is 33.47 plus 10.72 into eruptions, and again there will not be any error here because it is a fitted model now, okay. So, this Wi hat is nothing but similar to Yi hat, so fitted response, okay. Alright, now how do you interpret these two numbers is again important, right. I mean again couple of sessions back we discussed exactly this. So, how do you interpret B0 and how do you interpret B1, okay. So, firstly how do you interpret let us say 10.72, which is slightly more important to us. So, the first point here, for every 1 minute increase in the eruption time, namely EI, okay, for every 1 minute increase in the eruption time, the waiting time between the next eruption, the current eruption and the next eruption increases by 10.72 minutes, okay. So, what do you mean by this? This is a very important information in the context of the problem here, that if any eruption happens to increase even by just a single minute, right, then the next eruption waiting time increases by 10.72 minutes, okay. This is what 10.72 means, and the second, which is more the intercept 33.47, means the second bullet point. If the eruption time is 0, again 0 means what? Very small. So, let us say not even half a minute, right. So, if the eruption time is 0, the waiting time is around 33 minutes, okay. So, let us say if you see an eruption, but that eruption is so small, which is close to 0, very small, maybe a few seconds only, then you will see the next eruption in almost around 33 minutes. So, not a very long duration, okay. Anyways, but the idea is that once you create this fitted model, how should you interpret B1 and B0 in the context of the problem there, which is more important, okay. Alright, now lastly prediction. So, can we do some prediction now? The answer is yes. So, we have a small problem here. So, predicting the waiting time for eruption duration of 3 minutes. So, let us say if you fix the eruption duration to 3 minutes, let us say a particular eruption is worth 3 minutes of eruption, then what would be the waiting time for the next eruption, or how much is the waiting time until the next eruption. So, what you have to do is you take the fitted model on the last slide, you simply input 3 in place of EI, right, and then you solve. So, 33.47 plus 10.72 multiplied by 3, the answer is 66.66. What do you mean by this is that if the current eruption duration is around 3 minutes, then the waiting time until the next eruption is 66.66 minutes there. Okay. All right. Now, lastly, model visualization. So let's say, so again, this red line is exactly what we are trying to draw a short while back, but this is the exact line of best fit given by the fitted model. All right. So eruption and waiting time. Again, you have a scatter plot, and then this red line is nothing but Wi hat, or rather the line of best fit there. Okay. And again, like I said, a lot of conclusions can be drawn just by sort of simply fitting the red line on top of any scatter plot. So again, you can see the scatter among the points and the closeness to the line, etc., etc. So here, I can clearly see a lot of different things. So you don't have any outliers here, right? Variance is somewhat constant. Then fit is also decent. We have also proved that from the summary table, R square values, etc., etc., right? So again, all these checks are kind of pointing to the same direction that, okay, so EI is indeed a good predictor of WI, or the eruption duration is indeed a good predictor of the waiting time there. Okay, so now the last example, which is slightly more interesting because we'll delve deeper into MLR. We haven't discussed this in theory, but then how do you extend this to, let's say, if you bring in more than one X variable? Okay. So again, a slightly interesting data set called as the air quality data set. So again, this data set is inbuilt in R, and what this gives you is that the data gives the daily air quality measurements in New York between May to September 1973. So slightly old data, but again, it sort of gives you the daily air quality measurements in New York, USA between May to September of 1973. And this entire data frame contains 153 observations on 6 variables now, okay, and namely all these. So ozone, solar, wind, temperature, month and day. Okay, so ozone levels, solar levels, some sort of solar radiations probably, wind in miles per hour, temperature in degrees Fahrenheit, months 1 to 12. So which month of the calendar year you have, whether January or February and so on, and day of the month from 1 to 31. Okay. So now we'll see that out of all the 6 variables, which we can sort of pick as predictors and which variable can we pick as the response. So again, just a snapshot of the data set. Again, many more rows are there, so dot dot dot, but then these are all the columns. So ozone level, solar intensity, wind, temperature, month, day. So when you say 5, it means May, right? And of course you have 1, 2, 3, 4 up to 10 and many more. So and then temperature 67 degree Fahrenheit, 66 degree Fahrenheit, etc., etc. And for 14.9 miles per hour in terms of wind, and so on and so forth. Okay. So again, before we begin with MLR or any regression modeling, we'll do some exploratory analysis through scatter plots. All right. So again, 2 different scatter plots you have. So on one hand, you have temperature versus ozone. On the other hand, you have wind versus ozone. Okay. So again, one small assumption is that we can sort of treat ozone as a response variable here, while we can take wind and wind plus temperature as my x1 and x2 variables. Now again, remember this is an MLR problem. So MLR means more than one x variables. Okay. So here, more interestingly, is that we are trying to find out whether the significance of wind and temperature is there to sort of predict the ozone level in the environment. Okay. So we are not focusing on a single x variable, but multiple x variables here, namely wind and temperature collectively. But before we actually fit any model, we should always do a simple exploratory analysis through some scatter plots, some other plots maybe, and so on and so forth. So on the left hand side, you can see that a simple scatter plot between temperature and ozone, you can see an increasing trend there. Similarly, if you compare wind and ozone, you can see a decreasing trend. So again, all these conclusions can be drawn there. Okay. For example, in temperature versus ozone, you can see a small curvature possibly. So a straight line might not be very efficient, while if you see wind versus ozone, I can still draw a straight line even though you see a small curvature. So things are sort of left to analyze a bit further down the line. Okay. All right. Now the key point is fitting the MLR model. So how do you fit the multiple linear regression model? So the problem is that the researchers want to know how does the ozone level in the environment react to temperature variable and wind measurements in the environment. So we can create this MLR model. Now again, creating the MLR model is just a simple extension of the SLR model, and you'll see what we're doing here. So we're taking the response as the ozone level equals beta naught plus beta 1 into temperature plus beta 2 into wind plus the random error. So you have 2 x's here. So these are my xi variables, and then you have a single variable yi, which is nothing but the ozone level. Okay. And how many parameters you have now? So you have 3 parameters. So an intercept beta naught, you have beta 1 and you have beta 2. So again, the exact similar summary table, I will sort of skip a lot of ideas now. So we are not concerned about residuals, but we are more concerned about the coefficient table there. And here you can see that you still have an intercept and you have values or other estimates for temperature and wind separately. And ultimately you have p values for both wind and temperature separately. Okay. And of course you have ANOVA down the line and a corresponding p value there, etc., etc. Okay. So these are the estimates. So using these estimates, I can write down the fitted regression model completely, and using the p values in the last column, I can sort of test individually for the significance of individual variables on ozone. For example, if you look at the p value corresponding to temperature. So again of course both the p values are quite small, less than 5%. So 5.29 into 10 to the power minus 11, which is very, very small. So if p value is small, we can sort of conclude that the temperature variable is significant in predicting the ozone level, given that the effect of wind is constant in the model. Okay. So this is a small change you have to introduce in the MLR conclusion, the time when you conclude from the p values. I will repeat, I will take the second p value now. If you take the p value corresponding to wind, again the p value is significant. So we can see that there is a significant relationship between wind and ozone level, provided that the effect of temperature is constant in the model. Okay. Alright, so this is exactly how the fitted model looks like. So minus 67.32 plus 1.82 into temperature minus 3.29 into wind. And again, how do you interpret, right? For example, how do you interpret 3.29? So for every 1 mile per hour increase in the wind speed, the ozone concentration decreases by 3.29 ppb, parts per billion. So, and why decreases? Because you have a negative sign here. Okay. On the other hand, for every 1 degree increase in the temperature, 1 degree Fahrenheit increase in the temperature, the ozone concentration increases by 1.82 ppb. So all these interpretations were clear when we saw the couple of scatter plots earlier, right. So on one hand you had an upward trend, on the other hand you had a downward trend there. Now ultimately prediction. So predicting the ozone concentration when you fix couple of values. So let's say you fix wind speed to be 10 miles per hour and you fix the temperature to be 85 degree Fahrenheit, you simply take the fitted model, you feed in the values here, so 85 here and 10 there, and then you solve, and the answer is 55.07. So whenever my wind speed is 10 miles per hour and temperature is 85 degree Fahrenheit, my expected or rather fitted ozone concentration in the environment is 55.07 ppb there. Okay. And lastly, how do you visualize? Couple of plots to simply visualize the model. So now, since it's an extension of SLR, what we try to do is you can see 3 axes there, right? So this is my response axis, and then this is one of the variables, this is the other variable. And now, rather than fitting a straight line, I have to fit a plane, right? Because now imagine that you have multiple variables now. So it's no longer a single dimension or 2 dimension problem. It's a 3D problem because you have one response variable and 2 predictor variable. So similar to how you fit that red line or line of best fit, now we have a plane of best fit. And lastly, some diagnostic plots. So on one hand, you have residual versus fit value. So again, I can clearly see that you do have some problems, right? I mean, here, let's say you can see some curve here, right? The points are not evenly scattered around the 0 line. So there might be some linearity problems, there might be some equal variance problems, etc., etc. And on the other hand, this is more like a normal QQ plot. So this thing called as normal QQ plot, and you can see that there is some deviation on one of the tails. So distribution may not be entirely normal also. Okay. So when it comes to line assumptions, you do see some problems here. So what would be a solution there? You can transform. So you can transform either x, either y, or both x and y, and then refit the model and then move ahead. Okay. Alright, so just to summarize where we are at, that extending SLR to MLR is not very difficult, so anybody can do it. I mean, it's just that you are bringing in extra variables there in terms of x values, and then you can keep on extending howsoever many x values you have or you want. So x1, x2, x3, x4, etc., etc. down the line, refit the regression model, check for assumptions, and ultimately conclude based on the t-test p values or the overall ANOVA p value. Thank you.